Alright, so I'm back. I got interrupted the last time, but we're gonna pick up right where we left off. So we have our graph, and we're moving along. And I was talking about what if we tried to do the change in x or change in y over change in x equation, but with increasingly smaller, you could say, intervals. So what if my change in y was really, really small, and my change in x was also really, really small? At that point, it gets to a well, at those values, it gets to a point where it doesn't really change what the output is because it's so infinitesimally small. I mean, 3.000 and then 20 more zeros, 0.01, and then it changes to 3.20 zeros 2. That's such a small change that it doesn't really matter. And that's how we know we have our derivative on the graph. So when we talk about limits, it's because we're just calculating the change in y over change in x in increasingly smaller intervals until we get to there. It's as it approaches. That's why I use the terminology as x approaches certain value, as x approaches a in limits, because that's what this is. As x approaches a, what is the value? And that's our derivative. So the second part of this is, I don't have my key with me. I'm going to pause this. Okay, so here's our next example. I'm going to erase all this, and we're going to do a new graph with one more example, so you can visualize it again, and then we'll be done. So, let's say I have this. Let's say my function looks like this. It's just essentially a circle or a curve. Now, let's think about our derivatives. Think about the steepness of our tangent line. We're going to have equal points. We're going to have 1, 2, and 3, 2, and 3. So I'm also going to put one in right here just for a future thing. So look at this. What do you think at first? Well, let's look at the slope. It looks like the rate of change here is very steep. Like the distance we cover from here to here is way bigger the distance that we cover in from here to here. This is the same amount of like distance on our x-axis, but it's a very disproportionate amount on our y-axis. That's kind of another way to look at how our rate of change is changing, or the rate of our rate of change. So, tangent lines again, right here, very steep. I'm going to put this one at 20. This is less. This is 10. And if we're assuming these are equally spaced, this is going to be 0. This is going to be negative 10. Like if we have a tangent line that's going like this, that's negative 10. And this is negative 20. Now, you remember from our last example that we put all these points onto another graph, and they showed us a new graph, a new function that was consistent. So let's do the same thing again. Draw new graph. It's going to be essentially the same, but we're going to say time here is negative 1, 2, 3. So negative 2, negative 1, 0. Pretend that's where it goes. Negative 1. No, it's just 1 and 2. So this is essentially x equals 1. X equals 1 right there. Just for the sake of this. I know they're rough drawings, but I hope it makes sense. And we're going to draw it again. So let's plot our points at x equals negative 2, negative 1, 0, 1, and 2. So at negative 2, we have negative 20. So that is going to be x value negative 2, comma, negative 20. We're going to do it again. This is going to be negative 1, 10. Negative 1, comma, 10. And then at 0, we're going to get 0. And then at 1, we're going to get 10. And then at 2, we're going to get 20. Actually, hold on, I did this wrong. It should be flipped. That's my bad. At negative 2, it's going to be 20. At negative 1, it's going to be 10. At 0, it's still 0. At 1, it's negative 10. And 2, it's negative 20. So what does this look like on the graph? It is a straight line. Interesting, right? So I hope that makes sense. You can do this with virtually any graph. You can look at it and you can put or impose a tangent line on top of it, and boom, you're going to have your derivative at that certain point. And then if you plot the derivatives of different points, you'll have a graph that is essentially what you can use to find your derivative. Like I now have this function, which is essentially y equals negative 20x, and I can use this to find the derivative of any point on this. Like if I want to do negative 0.5, I can plug in negative 0.5 is x here, negative 20 times 0.5, and my result will be the derivative at this point, at negative 0.5. Simple as that. Anyways, that's the end of this little tutorial, the introduction to derivatives, and we'll be moving on in the next video to a definition of a derivative. Okay, I did actually forget one thing. Yeah, I did forget one thing. After you have your trig identities, you have your inverse trig identities, and that's an entire other ballgame. It's just more memorization, but there's a pattern, so you don't have to freak out. Let's see where it go. Oh, here it is. Yeah, so for each one, there's a pattern. I'm just going to write it down here because I don't have these memorized yet. Inverse trig. Sine negative 1 of x, and then cosine negative 1 x, tangent x, cosecant negative 1 of x, secant negative 1 of x, and then cotangent of x. So we're going to start with our sine. When you see this, it just turns into 1 over the root of 1 minus x squared. 1 minus x squared. Cosine is just going to turn into something similar, where it's negative 1 over the root of 1 minus x squared. Tangent is where it gets interesting, 1 over 1 plus x squared. I'm pretty sure, yeah. And then cotangent is next in line. Just because they're similar, it's going to be negative 1 over 1 plus x squared. And then the cosecant and secant are going to be interesting because it's going to just be the same as their original ones, like the same as these, but on the denominator, you're going to multiply the denominators by the absolute value of x, or which is your function. So this is going to become sine 1 over absolute value of x, or absolute value of your function, I think, times root of 1 minus x squared. And then same here, negative 1 over absolute value of x, root 1 minus x squared. And it's just that. So there are your identities. They're long. I don't think they're going to be tested a lot, thankfully. So